the moving of the fluid from one location to the another. In the convection heat transfer, the bulk mass of the fluid is moving from one location to the another. This movement or this transport of mass might happen naturally due to the density variations occurring due to temperature changes during the heat transfer, or sometimes we might have to provide some velocity to the fluid over the hot plate when the fluid is moving. That velocity may be provided by a fan or a blower or a pump. In the convection heat transfer, basically the fluid would have certain velocity as it is exchanging heat with the any solid body, maybe giving the heat or receiving the heat. This velocity usually provided by a fan in the case of forced convection heat transfer, whereas in the natural convection heat transfer or free convection heat transfer, the motion of the fluid would happen naturally due to the density changes and the resulting buoyancy forces. That is, a high temperature fluid will have a lower density. It will be moving up due to the buoyancy forces, whereas the low temperature fluid will have greater density. It will be occupying lower positions. So, convection heat transfer can be broadly divided as forced convection heat transfer, other is free convection heat transfer or natural convection heat transfer. In the forced convection heat transfer, the motion of fluid or the mass transport of fluid is provided by an external agency like fan or blower or pump, if in the case of liquids. Like this, if you are taking a flat plate, the motion of the fluid is provided by an external agency. In the case of natural convection, the motion or fluid occurs naturally without any external agency due to density changes happening due to temperature changes during heat transfer with a solid boundary. Like if this is a vertical wall, hot plate, hot vertical wall, the motion of the fluid will be like this. The displacement of the fluid happens due to density variations of the fluid. Whereas in the case of the forced convection, if this is the hot plate, the motion is provided by some external agency like a fan or a blower, where V infinity is the free stream velocity. Naturally, we can expect a higher convection heat transfer coefficient in the case of the forced convection, and hence higher heat transfer rates. It's very naturally expected that a hot body, if you want to cool it quickly, we will try to keep under a fan or under a pump if you want to cool the solid body abruptly. Whereas if the hot body is left to its fate in a natural environment, obviously it would take more time to get cooled because the convection heat transfer coefficients are lesser in the case of natural convection. So if you take a hot sphere kept in a still air or ambient air, this is the motion of the fluid pattern. This is the pattern of the motion of the fluid. If this is the hot sphere, this is the fluid or air. If there is a hot horizontal plate, this is how the motion of the air. In the case of the natural convection, this is natural convection. This is hot plate. This is also natural convection. So whereas this is boundary layer in the case of the forced convection, hydrodynamic boundary layer. So except the first figure where a fan is providing high velocity air over the hot plate, the remaining three figures are showing the examples for natural convection or free convection, where the fluid motion is upwards, because once the fluid picks up the heat from the hot solid boundary, its temperature increases, hence density decreases, because P by rho is RT for air. As the temperature increases, density of the air will decrease, air becomes lighter, the hot fluid moves up because of the buoyancy forces. The gap or the vacuum left over by this movement is filled with colder and low temperature fluid, which in turn takes the heat and moves up. That is how the convection currents proceed. Both the methods of heat transfer are governed by the Newton's law of cooling, which states that the rate of heat transfer by convection is directly proportional to the area of convection heat transfer and also the temperature difference between the solid body and the surrounding fluid. Both the modes of heat transfer are governed by Newton's law of cooling, that is, the rate of convection heat transfer is equal to HA delta T, so many watts, or otherwise HA temperature of the wall minus temperature of the plate. TW is the temperature of solid surface and T infinity is the temperature of fluid. H is the convection heat transfer coefficient in watts per meter square Kelvin. Now I shall give some numerical values for the range of the H. In free convection or natural convection with the gases like air, H will be varying between 3 to 25 watts per meter square Kelvin. In forced convection with gases, H values may vary between 15 to, in forced convection with gases like air, it may go up to 15 to 200 watts per meter square Kelvin. In free convection with liquids like water, the variation of H may be between 80 to the 250 watts per meter square Kelvin. In forced convection with liquids, the values may be between 100 to, it may go up to 2000 watts per meter square Kelvin, 2500 watts per meter square Kelvin, whereas H in boiling water, pool boiling or a flowing in a tube, the H values will be 3000 to 5000 to 50,000 watts per Kelvin, meter square Kelvin. H in condensation will be, condensation of water vapor will be 4000 to 10,000 watts per meter square Kelvin. So we are seeing that convection heat transfer coefficients are highest in boiling water case. Now I want to take the application of the dimensional analysis in the analysis of convection heat transfer. So let me state what is first of all Buckingham Pi Theorem. In fact, this is a mathematical technique used in hydraulic machinery, fluid mechanics, and also in the heat transfer. This theorem states that if in a functional relationship, if there are n number of variables, both dependent and independent put together, and if all the variables could be expressed in terms of m number of fundamental dimensions in toto, then the functional relationship could be written in terms of n minus m number of dimensionless pi terms. So I want to state the theorem like this. If in a functional relationship, if there are n number of total variables, both dependent and independent put together, and if all the variables could be expressed in terms of n minus, in terms of small m number of fundamental dimensions, then the functional relationship could be expressed in terms of n minus m number of dimensionless pi terms. I repeat the theorem. If in a functional relationship, if there are n number of variables, physical quantities, And if all the variables could be expressed in terms of smaller number of fundamental dimensions like mass, length and time, temperature, etc., then the functional relationship could be expressed in terms of n minus m number of fundamental dimensions. This is a very useful theorem, particularly in the convection heat transfer. In forced convection heat transfer, where velocity of the fluid is provided by an external agency, the convection heat transfer coefficient is function of V, D, rho, mu, Cp, K, where V is the velocity of fluid flowing past the solid surface, D is the characteristic dimension, maybe length or diameter of the body, rho is meters, this is velocity is in meters per second, rho is density of fluid. Mind that rho is density of the fluid in kg per meter cube, mu is coefficient of dynamic viscosity of fluid given in Pascal second or Newton second per meter square or kg per meter second. Cp is specific heat of fluid in joule per kg Kelvin, and K is equal to thermal conductivity of fluid in watts per meter Kelvin. These four are thermophysical properties of fluid which are assumed to be constant at a given problem, because even though they are variables of temperature, we will be taking these properties at the bulk mean temperature of the fluid, that is usually the average temperature of the plate and the fluid. At the mean temperature of the plate and the fluid, we will be taking these properties of the fluid. V is the velocity, D is the dimension, characteristic dimension. In this above functional relationship, how many variables are there? Total number of variables, physical variables, in the above functional relationship is equal to n is equal to, including dependent, h is a dependent variable, remaining 6 are independent, total is 7 number of variables are there. So how many total number of fundamental dimensions in which all the variables in toto could be expressed? That will be m, that will be 4 here. What are the 4? Mass, length, time and temperature. Please, I want to mention here that each physical quantity may not have all the 4, but in toto all the number of fundamental dimensions are 4. H may have time, rho may not have time, etc. But in toto there are total number of fundamental dimensions are 4. Hence, from Buckingham Pi Theorem, the number of dimensionless pi terms is equal to n minus m, that is 7 minus 4, 3. Therefore, the functional relationship, let the pi terms be pi 1, pi 2 and pi 3. Hence, the functional relationship among the variables could be written as pi 1 as a function of pi 2 comma pi 3. This is the use of Buckingham Pi Theorem. From the Buckingham Pi Theorem, in the case of forced convection heat transfer, pi 1 is obtained as vedi rho by mu. This is a dimensionless quantity which also known as Reynolds number. Very important number in fluid mechanics, also defined as inertia force divided by viscous force. If Reynolds number is less than 2000 in pipe flow, like this, V is the velocity, D is the diameter, rho is the density, mu is the dynamic viscosity. If the Reynolds number is less than 2000 in pipe flow, then flow is considered as laminar flow. If Reynolds number is greater than 4300 in pipe flow, then flow is turbulent flow. If 2000 less than RE, Reynolds number less than RE is abbreviation of Reynolds number, less than 4300 means flow is in transition. For flow over flat plate, the another important case of convection heat transfer, if V infinity is the free stream velocity of fluid, this is the hydrodynamic boundary layer. This is the X, direction of X. This is called leading edge. The other end of the plate is called as trailing edge. At any X measured from leading edge, let X is equal to distance measured from leading edge. then local Reynolds number is defined as V infinity into X into rho by mu, which can also be written as V infinity into X by nu, where nu is equal to kinematic viscosity defined as dynamic viscosity divided by density, having the units of meter square per second. This is called local Reynolds number, V infinity into X into rho by mu. In flow or flat plates, if REX, local Reynolds number, is less than 5 into 10 power 5, implies flow is laminar flow. And if REX is greater than 6 to 7 into 10 power 5, implies flow is turbulent flow. Most of the cases in the pipe flows, the flow is considered to be turbulent, because once the Reynolds number crosses 4300, the flow would become turbulent. Whereas in the case of the flat plates, rarely the flow would be turbulent, because till 5 lakhs, till the Reynolds number value of 5 lakhs, the flow is maintained as laminar. That is, usually the flows are laminar over the flat plates, and usually the flows are turbulent in the case of the flow through pipes. So please mind this particular point there. Then the pi 2 in the dimensional analysis is nothing but Nusselt number, which is defined as HD by K. Please note that here the K is the conductivity of the fluid. This resembles this Nusselt number is abbreviated as Nu, resembles Biot number in unsteady state or transient heat conduction. But in Biot number, this is conductivity of the solid, which is the criteria. The value of the Biot number is the criteria for lumped heat capacity analysis. We have seen already. Pi 3 is the other third number in the dimensional analysis. Pi 3 is Prandtl number, which is defined as kinematic viscosity of fluid divided by thermal diffusivity of fluid. What is kinematic viscosity? Nu. What is thermal diffusivity? Thermal conductivity by thermal capacity, that is K divided by rho Cp. Nu into rho Cp by K. The result is mu Cp by K, because nu into rho is dynamic viscosity. Please note that Prandtl number is property of fluid, whereas other two numbers, that is Reynolds number and Nusselt number, they are not the properties. Prandtl number is the property of the fluid, which is defined as the ratio between kinematic viscosity and thermal diffusivity. In fact, Prandtl number is the criteria. Later we are going to see that Prandtl number is the criteria which tells whether hydrodynamic boundary layer is thicker or thermal boundary layer is thicker. in the convection heat transfer problems.